Hi everyone, Mr. Holtgren here, and today what we're going to talk about is how we can predict the polarity of a molecule based on its shape. Okay, so now if we go back to the beginning, if you will, Lewis dot structures help us predict the shape, right? So we learned how to look at the number of valence electrons, and then that allowed us to build the Lewis dot structure, and that would then lead us to be able to identify what shape it is, right? So that's where we are right now. The next thing we want to look at is to determine or be able to figure out how does the shape then impact the polarity of the molecule itself, okay? Now you'll see down at the bottom here, it says that in symmetrical shapes, any polar bond or dipole moment, they may cancel each other out and then make the molecule nonpolar. So here's the key, is if a molecule is in 3D, if it's symmetrical, meaning that it does not have a positive or negative charge to it, it is going to be a nonpolar molecule. So for example, look at this here in the middle. So we've got carbon, and we have 4 chlorines around the outside. Okay, so these 4 chlorines around the outside, they do have a dipole, but it's like tug of war. They pull against each other and cancel each other out. So this molecule is symmetrical. Okay, so that's what you're going to look at to see if a molecule is going to be polar or nonpolar, is based on its symmetry. So a molecule that is symmetrical is going to be nonpolar. It doesn't have a positive or negative end. Okay. Now, this is tetrahedral, right? Tetrahedral. Now look at this one. This is also tetrahedral, but notice that it has a different atom up here. Okay. Now, because it has a different atom up here, this is asymmetrical. It's not symmetrical. And as a result of that, this molecule is going to be overall polar, okay? So it's going to have a concentrated negative charge here at partially negative end, and this other end down here will be partially positive. So that's really what we're looking for, positive, negative ends. Now, so it depends on the shape, and I'll show you some examples here in a minute, but look at linear. So here's an example of a linear one. Linear can be polar or it could be nonpolar. So look at the nonpolar. It's symmetrical, right? It's exactly the same on each side. So it is nonpolar. Whereas in this example, if we have hydrogen chlorine, it's not symmetrical. Therefore, it's going to be polar, okay? Trigonal pyramidal. Trigonal pyramidal, because of the unshared pairs of electrons, the lone pairs on top is always going to be polar. And then trigonal planar, this one here, again, this could be either one. Right now, this is nonpolar because look at the 3 branches. They're all the same. But if one of these branches was different, it would then be polar. Okay. Now here, take a look at this. So this is where we're trying to put it all together for you. We've got the 5 shapes up front, and then are they polar or nonpolar? Now, bent and trigonal pyramidal are always going to be polar. The reason why is because they have on top, they have got that lone pair of electrons, right? That unshared pair, the unshared pairs of electrons, they cause, and you can see in the 3D image here, they cause those branches of the molecule to get pushed away into the shape, okay? So bent and trigonal pyramidal will never be nonpolar. They always are going to have kind of a positive end, a partially positive end, and a partially negative end, okay? Now, the next 3 shapes, they could be either or. You have to look to see, are they symmetrical molecules or not? Okay. Now, for this example, for linear, right, and we kind of looked at this one already, but if you've got 2 different atoms, that's not symmetrical. So this would be polar, a polar molecule. Now, this is an example of one that is nonpolar, right, because it's symmetrical, right? It's the same on both ends. So it's not going to have a positive or negative end, so it's a nonpolar. Let's look at trigonal planar. Now, trigonal planar, maybe looking at the nonpolar one's easier to start. Now, because trigonal planar does not have those lone electrons on top, it kind of takes this orientation. And it's the same on every side, right? It's got the 3 points are all the same. So that's going to be nonpolar. It's not going to have a positive or negative end. But if you have, this one is also trigonal planar, but because, look, it's not symmetrical. Now we have this oxygen floating out at the end, so we're going to have this overall kind of negative charge down by the oxygen, and the hydrogen is going to be more positive. Okay, and then lastly, tetrahedral, it's kind of the same thing, right? If we look at the nonpolar tetrahedra, nonpolar, all 4 points are the same, right? So it's symmetrical. Whereas in this example, right, instead of having the 4 hydrogens, for example, on the outside, it has, look at that guy, it's got a 1 fluorine. So this guy's not symmetrical. So this one is going to be polar. So just remember now, polar is going to be from non-symmetrical or asymmetrical shapes, and then non-polar molecules are ones that are symmetrical, okay, where they're kind of the same across. All right, so I'm just going to show you guys a couple of examples here where we can look at the picture. So here's an example of, this is linear, right? But you'll notice that it's symmetrical, right? It's the same on both sides, no matter how we turn it here. And then if we put the electrons in here, you can see that blue is positive, red is negative. This doesn't really have any of that because it's non-polar, it's symmetrical as a result. Now, look, if we look at one that is not symmetrical, so here's hydrogen and fluorine, okay, and we can even go down here and look at the electronegativities, right? It's got these different electronegativities. But if we show the electrons, there you go. Look, see how the fluorine, because it's more electronegative, it has electronegativity of 4.0, is going to kind of hog those electrons. Okay, so this is going to be a really negative side, and the hydrogen side is going to be positive. So that's an example of how linear can be either or, right? Either or. Okay, let's look at a couple more here. So let's go ahead and look at one that is bent. Right? So where's water? There it is. Okay, so here's water. There's the bent shape. Now remember, it's not showing it here, but it has these electrons up top, the two unshared pairs of electrons that are causing it to have this bent shape. But then because, remember we said bent is always polar, right? This is why, right? So bent is always going to be polar. The other one we said that is always going to be polar is trigonal pyramidal, right? So the trigonal pyramidal, it's got the, again, you got to look for on the central atom. Does it have those unshared pairs of electrons? They're up here. And as a result, you get this, right? You get this a polar molecule. So bent and trigonal pyramidal are always going to be polar. All right, then let's look at just tetrahedral for the last one. So here's tetrahedral, right? And you can see here we've got carbon with 4 hydrogens. So it's the same no matter how you turn it, right? So this is symmetrical. So as far as polarity, it's uniform, right? It's does not have like a positive or negative end to it. Right? But if we look at a molecule that is not symmetrical, this is the one we looked at that previous page, right? Let's look at where the electrons are for this guy. Yeah, look at that now. So see the difference, right? Because this guy's not symmetrical, the electrons are not going to be all in the same place. They're going to be kind of congregating at one end. Okay, so big picture, right? What we're looking at here is Lewis dot structures allow us to determine the shape of a molecule, and the shape of the molecule allows us to determine the polarity of the molecule. And again, we're not talking about the bond that's inside of the molecule. We're talking about the molecule as a whole. Is the whole molecule polar or nonpolar? Okay, if it's nonpolar, it's symmetrical, right? It's the same kind of on every side. There's no positive or negative end to it. If it's polar, that's because if we have, it's asymmetrical, right? It's got something about it that makes it not symmetrical. And then as a result of that, it becomes polar, right? It's going to have kind of a positive and negative end. Okay? All right, let us know if you have questions. Rewatch the notes and talk to your teacher. Have a good day, everyone.